Before we master Gauss's law, we must master electric flux. Flux is simple in definition, yet surprisingly subtle in application. Today, we'll remove every confusion from this topic. Most books give the casual definition: number of field lines passing through a surface. A senior physicist's correction: electric flux is the measure of the field component that pierces a surface. It is a dot product, not a line count. Mathematically, d phi equals E dot d equals EA cos theta, where E equals magnitude of electric field, A equals area of the surface element, theta equals angle between E and normal to the surface. Important to note, flux is a scalar, but it can be positive or negative. Flux depends on orientation, not on shape. Whenever we calculate flux, we are asking, how much of the electric field actually cuts through the surface? If field is parallel to surface, no cutting flux equals 0. If field is perpendicular, maximum cutting flux equals EA. If field is at angle, only the cos theta component pierces the surface. This is geometrical physics, not brute memorization. A senior professor teaches this carefully. The angle theta is not between field and the surface itself. It is between field and the surface normal. Thus, case 1. Field perpendicular to surface, theta equals 0 degrees, flux equals EA. Case 2. Field parallel to surface, theta equals 90 degrees, flux equals 0. Case 3. Field at angle, flux equals EA cos theta. Common mistake: students use the angle between field and the surface instead of field and surface normal. Let's examine typical shapes JEE uses. A. Flat surface, phi equals EA cos theta. If surface is tilted, calculate area times cos theta, not area alone. B. Curved surface, take a cylinder in a uniform field. Flux through curved surface equals 0 y. Field is parallel to surface everywhere, theta equals 90 degrees. This is a favorite JEE trap. C. Hemisphere in uniform field, if field is vertical. Flux through curved hemisphere. Phi equals EA, flux through circular base. Phi equals EA, total flux equals 0. D. Cone surface in electric field, flux through cone. Phi equals EA cos theta, but remember, theta here refers to angle between field and the cone's normal, which varies. The simpler method, phi underscore cone equals E times projected area equals base area equals pi, are squared thus. Phi equals E pi are squared, elegant and very useful. If the surface completely encloses a region, field entering negative flux, field leaving positive flux, but total flux depends on charges inside. Right now, simply note, if no charge is inside, the net flux is 0. Negative flux indicates field is entering the surface, angle between field and surface normal is greater than 90 degrees. This is purely geometric, not physical negativity. Here are the styles JEE repeatedly tests. Q1. Flux through tilted square, a square of side L is placed in a field, making angle 60 degrees with its normal. Flux? Phi equals EAL squared, common mistake. Using sine instead of cosine because of angle confusion. Q2. Flux through the curved surface of a cylinder, uniform field along axis, flux through curved surface equals 0. Students often mistakenly calculate something non-zero. Q3. Flux through a cube in uniform field is along plus x direction. Flux through each face? Only two faces get flux. Face, positive EA face, negative EA all other faces. 0 net flux equals 0. Q4. Cone in electric field, flux through cone equals flux through its projection pi are squared E. This comes directly from geometry, not surface integration. Q5. Flux through closed surface without enclosed charge, JEE often gives a weird shape with multiple openings. But if surface is closed and no charge is inside, flux equals 0 regardless of field direction. Flux is a geometric concept. If you understand angles, projections, and surface normals, you will never struggle with flux-based problems again. This entire episode was preparation for Gauss's law, which becomes almost trivial once flux is mastered.